We get an underdamped response in second order differential equation when the characteristic equation, which is based on the homogeneous second order differential equation, results in a discriminant delta that is less than 0. In other words, that alpha is less than omega 0. That means this delta will be less than 0. And this particular term in here, since alpha is less than omega 0, this term in here will be negative, and I'll be taking the square root of a negative number. If that's the case, we'll end up with a couple of roots, and these roots in here, if we plot them on the S domain and we assume that this is real and this is imaginary, what we'll end up with is two complex conjugate numbers. So this one here, because this will be complex, well, let me just show you why it's a complex number, because we can assume, for example, S1 is negative alpha plus, well, negative omega 0 minus alpha squared, okay? Well, but we know the square root of a negative one is just simply, well, typically in math we call it I, but we're going to call it J in here because I is current. So if I combine these two in here, what we'll end up with is S1 is just simply negative alpha J squared root of omega 0 squared minus alpha squared, and S2 is just negative alpha, this one here is negative, or plus actually, sorry, negative J and the square root of omega 0 negative alpha squared. And these are complex conjugate, and that's what you see in here. And why did I put them in the negative here? Because the real part in here in both cases is negative, so they're in the negative in here. So they're complex conjugate, and if that's the case, we'll get what we call the underdamped response, and it's of this form, so it has oscillation. So let me show you why it has oscillation. So if we do a quick change of variable, and I told you, you know what, let's reterm omega d in here, and we'll say that this is simply the omega 0 squared minus alpha squared. So now this one here and this one here will be just simply omega d. So we'll get S1 is just simply negative alpha plus j omega d, and S2 is just simply negative alpha minus j omega d. And this omega d, by the way, is sometimes we call the damped. Okay, let me just do this here. It's the damped radian frequency. Okay, that's what we call it, the damped radian frequency. And anyway, so we'll end up with these two complex conjugate. While we have discussed that the complementary solution is simply k1 e to the power s1t plus k2 e to the power s2 of t, well, simply it's k1 e to the negative alpha e to the j omega d plus k2 e to the negative alpha e to the negative j omega d. Okay, well, this d is subscript, so let me just make sure it's clear. So this is a subscript d, this is subscript d. And I've forgot to multiply both of them. Well, we multiply because, well, let me just do this here, just so that it's better and clear. Okay, so we'll do this here, we'll do this here, we'll do this one here. Okay, and what we have is this is plus, okay, and all of this in here is multiplied by t, and all of this here is multiplied by t. So if I just do a little bit of algebra, e to the negative alpha t times e to the negative j omega d of t plus k2 e to the negative alpha t e to the negative j omega d of t. Well, what I have is I have this here, and this here is a factor that I can take out. That tells me e to the negative alpha t, k1 e to the negative j omega d of t plus k2 e to the negative j omega d of t. Okay, I believe that should be here a positive. This should be a positive here. And one of the most informative or powerful rules in engineering and in math is what we call the Euler's formula. Okay, and just as a quick reminder, okay, Euler's formula tells me if you have something like e to the j of theta, you can simply call it as cosine of theta plus j sine of theta. So what I will do is I'll take this here and apply it to this one and apply it to this one in here. So I'll just rewrite these e to the j. Well, I'm calling it j. It used to be I. Remember, the j is the complex, is the negative one. It's a complex number. Okay, and so we'll just rewrite these here, and what we'll end up with is the complementary solution is just simply e to the negative alpha t, and that here is k1. And well, let me just rewrite this one here because we're going to have different levels. That will be k1, and that one here is simply cosine omega d of t plus j sine omega d of t. Okay, plus that will be k2 times cosine omega d of t minus j sine omega d of t, because we have a minus in here. Okay, so we do a little bit of algebra. What we end up with is negative alpha t, and that will be k1 cosine of omega dt plus, I believe, k2 cosine omega d of t. And then what we have is the following. We have plus k2 j sine omega d of t minus k2. Actually, this one here is k1. Okay, minus k2 j sine omega d of t. Okay, so more algebra, e to the negative alpha t, that becomes k1 plus k2, and that here is cosine omega d of t, I believe, plus what we can say is this one here is j k1 minus k2 sine of omega d of t. And of course, if we do a little bit of change of variable, for example, we call this beta 1, we call this including the j as beta 2, what we'll end up with is the following. We'll end up with e to the negative alpha t beta 1 cosine omega d of t plus e to the negative alpha t beta 2 sine omega d of t, and that will be the complementary solution. Hence, we get the oscillation. So if you see it in here, and it's a dampened oscillation. So what we get is something that contains a cosine and sine, so there's oscillation with a frequency that is omega d, and at the same time, this oscillation in both the cosine and sine is being dampened by e to the negative alpha t. And that's, if you actually plot them, this is what you see. You see a little bit of oscillation at the beginning, and then eventually the oscillation just gets dampened out, and that's why it's called dampened radian frequency. Okay. So you might be wondering, well, can I really take this j to be included in that? And think about it. Well, I know that everything we have is real. So this is real, this is real, this is real, this is real, and I know that xt of t must be real, and this one here is real because k1 and k2 are real. That means j k1 minus k2 must be also real. Okay. All right, so what's left then? Well, what's left is the following. So this is a solution that really, it contains now, instead of k1 and k2 as in the overdamped response case, what we have is a couple of constants in here. So we need a couple of initial conditions for us to compute what these constants are. Again, what we can do is we can say, well, let's assume that t equals 0, and usually when you compute the initial conditions, you include the full solution. So you can tell me the x0 is just simply the particular solution evaluated at 0 plus e to the power 0 beta 1 cosine of 0, which is just simply 1, plus e to the power 0, which is 1 beta 2 times sine of 0, which will be 0. So this one here is just simply 0, and this one here is 1. Okay, so that tells me that x of 0, which is the initial condition I or v at 0, is just simply the particular solution evaluated at 0 plus b1. So that's the first equation that you can use to compute what b1 or beta 1, not b1. Okay. What about the second equation? Well, the second equation is, as usual, what we can do is we can say, well, if we do the dx of t divided by d of t and we evaluate it at t equals 0, what we end up with is the following. What we need is the full solution. Okay, and remember, it's like the full solution is x of t is just simply x particular plus xc, which is this big equation in here. So what we will end up with is the following. We're going to take the first derivative of dxp of t and d of t plus the derivative of the other part. And if you take this derivative in here, we'll have the derivative of this. You have to apply the product rule on this, and you have to apply the product rule on that. For the sake of time, I'll leave this as an exercise for you. And what I can tell you is the following. So in here, well, if we're talking about a particular solution for DC, that must be 0. So I'm just going to basically eliminate it. So the particular solution in DC only, it doesn't affect this. So what we'll end up with is the following. Negative alpha beta 1 plus omega d beta 2. Okay. And that is basically the second equation that you should be using. Again, the way I got to it is the following. I took the derivative of this and the derivative of that, but the derivative of the complementary solution contains a couple of functions of t, e to the power of t and cosine of t. So what we need is we need to apply product rule. The product rule tells me take the derivative of this, multiply by that, plus the derivative of the cosine, multiply by this, and you apply the same function in here, and you do a little bit of algebra, and then you substitute t equals 0. Whenever you have a sine, it will just disappear because the sine of 0 is 0. Whenever you have a cosine of 0, it's just going to be 1, and you'll end up with this equation. So these here are two equations and two unknown, which are beta 1 and beta 2. Once you figure them out, what you end up with is the complementary solution figured out, including beta 1 and beta 2.